Hello, my name is Oleg Chat, and this video tutorial is about vina, a program I wrote while in the molecular graphics lab at the Scripps Research Institute. I'm going to be using this structure that is a receptor that binds an anti-cancer drug called imatinib, and I will be using a randomized structure of this drug molecule and try to predict its bound conformation in the receptor. vina is the program that actually does the docking. It takes its input in the PDBQT file format, and I will be using Autodoc Tools as a program distributed as part of MGL Tools, also developed in our lab. MGL stands for Molecular Graphics Lab. vina produces output in the same PDBQT file format. I can use either MGL Tools or PyMol to view the results, and I will be demonstrating the use of PyMol for this. Note that I'm using this version of MGL Tools, which is the latest non-beta version as of now. I'm also using this older version of PyMol because it seems to be better at displaying small molecule PDBQT files for my purposes than the current version. This older version is available here. Before we begin, a few words about the theory. We are considering a system consisting of the receptor and the ligand. In water, I collectively refer to their degrees of freedom as conformation. For each conformation, there is a corresponding potential energy value. However, because we are considering the solvent implicitly, what we have is actually an energy-like quantity. It is often said that the global minimum corresponds to the native conformation. However, this is not quite correct. A deeper but narrower well may actually be less preferable because of the entropy. The quantity we are most interested in is called the chemical potential. It can be used to calculate the free energy of binding and the affinity of the ligand to the receptor. However, calculating the chemical potential from the first principles is very expensive computationally. What docking programs generally do is they use a scoring function, which is a function tuned to recognize the promising conformations and to predict the affinity as much as possible. This said, let us begin the actual demo. I'm going to start Autodoc Tools. And I'm going to separate the dashboard widget so that both of the windows can fit on my screen. File, Read Molecule, My Documents, vina tutorial. This is where I put the input files for the tutorial. I'm going to open protein.pdb. Most PDB structures do not have hydrogens, and we have to add them with edit hydrogens, add polar only. OK. Now Autodoc Tools added all the polar hydrogens. They are required by the PDBQT file format. I can use the dashboard widget to display the molecular surface. Or hide it. Or color the atoms by their type. And so on. I'm going to click Grid, Macromolecule, choose Protein, select Molecule. OK. And I'm going to save the protein PDBQT file in the same directory. Grid, grid box. We have to choose the part of the receptor where the docking program will be looking for docked conformations of the ligand. This is called the search space. I can move the receptor with the right mouse button. I can also rotate it with the middle button and move it closer or farther away with the scroll wheel. In fact, I don't have a middle button, and clicking on the scroll wheel works the same way. For the center of the search space, I'm going to use these values. 11 for X, 90.5 for Y, and 57.5 for Z. Sometimes you have to hit enter to update the view. We also have to choose the sizes of the search space. Autodoc Tools measures the sizes in points instead of angstroms. To convince it to use angstroms, we can set this dial to 1.0, which is a scaling factor. For the sizes, I will use the following values. 22 for X, 24 for Y, and 28 for Z. I don't have to save anything here. This step is just to visualize the search space. But I have to remember these values to use them directly with vina later. Now let us open the ligand. Ligand, input, open, my documents, vina tutorial. Ligand.pdb. Okay. We can hide the protein so that we can see the ligand better. I recommend using ligand structures that already have the correct hydrogens. This way, when you open them using Autodoc Tools will automatically merge the non-polar hydrogens and leave the polar hydrogens needed by PDBQT. Now let us look at the rotatable bonds in the ligand. Ligand, torsion tree, choose torsions. Autodoc tools colors the rotatable bonds in green and the non-rotatable ones in this color. We can make these bonds rotatable by clicking on them, and I'm going to make this bond rotatable next to the aromatic ring. Now we have 7 rotatable bonds and 1 non-rotatable bond in the middle. I'm going to click Done and save the ligand structure as PDBQT. Now we can close ADT because we don't need it anymore. We're almost ready to run vina. Start, all programs, accessories, command prompt, and change the directory to my documents, vina tutorial. Vina is installed by default under Program Files, the Scripps Research Institute, vina. I'll use this option --help to print the other options. As you can see, vina requires the names of the files for the receptor and the ligand. I can use this option to specify the receptor file, protein.pdbqt, and so on. However, sometimes it's more convenient to use a configuration file. Let us create one. Start, My Documents, vina tutorial, New, Text document, and I'll call the configuration file conf.txt and put the options in there. Receptor is protein.pdbqt, the ligand is ligand.pdbqt. The geometry of the search space is you may remember, center X is 11, the Y coordinate of the center is 90.5, the Z coordinate is 57.5. The sizes are 22, 24, and 28. These are all the required options. Vina produces one or more binding modes as its output. Each of the binding modes goes into its own PDBQT file, and the names of the files are determined by the name of the ligand. Sometimes it's more convenient to put all of the binding conformations into one multi-model PDBQT file. For this, we can use the option all, and we'll call the file all.pdbqt. Another important option is exhaustiveness. By default, it equals 8, and exhaustiveness determines how exhaustively the search algorithm looks for the global minimum and other binding modes. It is the exhaustiveness parameter is roughly proportional to the time the algorithm takes. The longer it runs, the less likely it is to fail to find the global minimum. As a programmer, I could not choose one value appropriate in all cases. You might be doing virtual screening when the CPU time is very valuable to you, or you might be docking one ligand when you can afford to spend more CPU time. In this case, we'll just accept the defaults. I'm going to run vina by providing it the configuration file name. I don't have to put all of the options in the configuration file. I can specify that the log file, there should be a log file, and it should be called log.txt. Now I can run vina by hitting enter. I fast-forwarded the program for you by pausing the movie encoding. It should actually take, program run at these settings should take about a couple of minutes if you have a modern quad-core computer. Longer if you have a slower machine, of course. By the way, vina automatically detects the number of CPUs or cores you have and takes advantage of them to speed up the search. Those of you familiar with Autodoc may have noticed that vina does not require you to pre-calculate the grid map files or to supply to determine the atom types in the grid maps. It calculates its grid maps automatically after it starts, and because it does it rather quickly, there is no need to save or read them from files. When vina finishes, it prints the binding modes it found, in this case 3, and the corresponding affinity values. It also produces the output files. As you can see here, there are 3 new files for each for its own binding mode. Also, it produced the all.pbkt file with all of the binding modes in one. We can open this file using pymol. We can cycle through the binding modes using the arrow keys. The first binding mode is the best one according to vina. Let us also open the receptor file. protein.pdb. experimental structure. As you can see, the first binding mode that vina determined is actually quite close to the crystallographic structure. Let us the receptor to see them better. Vina was able to do this even though all the rotatable bond torsion angles and the orientation of the ligand as well as its position were randomized. It could do that because the scoring function correctly identified the native conformation as the global minimum, but also because the search algorithm was able to find the global minimum. The search algorithm is stochastic, however, and with these settings for this input, there is some probability that it will not be able to find the global minimum. I think it's about a few percent in this case. The exhaustiveness value, as we discussed, determines a compromise between how exhaustively the search looks for the global minimum and the speed of the search. Increasing the exhaustiveness can dramatically decrease the probability of failing to find the global minimum. Well, this is it for now. I would like to thank people in the molecular graphics lab for their input, and especially Stefano Forley for his help with this tutorial. Bye-bye.